perhaps it's the customer bank balance. Now we rearrange the rows so that the rows are sorted by the customer bank balance. So you see 350, 400, 500, 600, and so on. For you now, in the year 2020, this probably is like a trivial idea. Yeah, sure, what about sorting the data? But the point is, try to think of this being in 1950s or 1960s. At that time, scientists were still exploring how to work with a huge volume of data. Prior to the computer, everything was done on paper books or accounting books, and there is no notion of moving things around. You insert an entry according to the time of arrival, by date. Customer deposits an amount or opens a bank account today. He will be giving a serial number in today's ledger or today accounting books, and the value is inserted as of today. There was no sorting of entries in a ledger or in an accounting book or in a bank records. But now we can sort things, we can change the order. So this became a very important idea because computer scientists realized that actually once you get the data sorted, you can do some really interesting stuff with it. Okay? In fact, if you go back to your CS3 data structures and algorithms course, we taught you if the data is sorted, you can do binary search. And if you can do binary search, you can enhance the performance significantly. And instead of doing linear search in O of n, now you can do it in log n. Okay? So the idea of sorting also comes from the database world. But once you sort the data, you run into all kind of issues. Okay? For example, how do you insert now? Well, we have to insert the row in the right location to keep the data sorted. What if you insert in the middle and there's no space where you want to insert? Let's say you get an entry with the value 15 and you have 10 and 20. You would like to insert the 15 between 10 and 20. But 20 comes immediately after 10. There's no space. So you end up shifting down one row to be able to insert the 15. Okay? What if you have applied the scheme we discussed earlier, which is dividing the table on these 2 pages or blocks, where you store part of a page or block, part of a table in each one of those blocks or files. So you got to find the right page or block to insert the 15. What if you go there and you find that the page is full of rows? You've reached the maximum capacity of the page. Now you got to figure out how to do it. You got to take the last row in that page and move it on to the next page to be able to insert your new row. Now what happens with deletion? If you delete in the middle of a set of rows, you will end up back with the defragmentation problem or the fragmentation issue that is solved through the defragmentation process. Okay? So this should give you a hint to something that will come up over and over in this course, and it's actually one of the main ideas that you need to understand. That when you have a set of related operations, in this case insert, delete, and search, if you speed up or if you design for one operation or if you speed up one operation by designing the data structure or the storage to support the fast version of this operation, like in this case, if we sort the data, we can do something like binary search. So instead of doing linear scan, we can get it in log n. So we're really designing for searching. If you speed up one of the operations, it almost guaranteed, but not necessarily always the same, but it's always, I would say it's most of the time, you will slow down the other operations. And that's what you see here. If we sort the data, search is fast, but insertion and deletion gets penalized. And there are other data structures that you might learn about in the future, where if you do the insertion fast, most likely you are affecting the search or the deletion or both. Okay? So there is always this trade-off. given any set of operations that work on the same data structure or in the same data, if you speed up one, the others are penalized. Now, another very big idea that comes from the 60s is creating an index. This notion that we're going to create another data structure, not the table, not the relation, not the pages of the table or the relation, but something else. And we search or we work with that something else, which is this data structure or index, instead of working with the table directly. Okay? The two main ideas up till now that really stands out, that will continue with us up till today, is that the table content is divided into pages, which is mapped to some kind of disk blocks. We'll talk more about that later on. But now we're dividing, from now on, we'll always think of dividing the table into pages. So while conceptually we would think of it as one big table, or one table, or which corresponds to one entity that you've identified in your system analysis and design exercise at the beginning when you were designing the database schema, internally this is cut into smaller pieces. That's one major idea. And the other major idea is that we are going to create something else beside the table. We're calling that the index, and we work through the index, or using the index, to do all kinds of operations on the table. Now, where is the index ideas coming from, by the way? Well, unfortunately, you haven't seen this, or perhaps it's fortunate, but I can tell you where an index is coming from. It's coming from a library index. So the question is, what's a library index? Well, you're not seeing that. That's why I'm saying unfortunate or fortunate, depending on how you look at it. Historically, libraries that had millions and millions of books, was very difficult, actually, to locate any particular book when you're inside. Okay, let's say you go to the Library of Congress. In fact, I don't need to tell you about the Library of Congress. I could tell you about the library of my undergraduate studies. I did my undergraduate studies in the AUC, and the AUC then was the largest library in Egypt. It had about 300,000 books. The AUC library, then it was in downtown, was basically a building that occupied 4 floors. There were books spread out on 4 floors. So if you'd like to find any particular book, it's actually quite difficult. You will end up walking in aisles and aisles of books, endless books, 300,000 of them. So the way it worked is, in the first floor in the library, you will find a cabinet that had very small drawers, and the drawers are labeled with letters, A, B, C, D, and so on. And if you're looking for books about computer science, you would go for the drawer that has the letter C. When you pull that drawer, you will see cards. 1 card for every textbook in the library. Then you have to flip with your fingers through the cards to find out all the books, or skim through all the books they have that is labeled a computer science textbook, until you find the book you're looking for, or a candidate book. And then you will find its location. They will tell you on the card, it's the 2nd floor, aisle number 15. So you go to the 2nd floor, aisle number 15, and you start looking for the book. This is the idea of a library index. Okay? And that's what influenced database designers. They must have got exposed to that when they were studying in the university. Everyone was using, in the past, library indices. Okay? So the idea is you use something to go faster to what you're looking for. Okay? This is what an index is all about. Now, the first type of an index that was invented was called a primary index. The primary index is an index you build on the primary column. And the primary column is the column used to sort the rows. Okay? So again, I'm assuming here the relation is sorted on some column. For example, in the table that shows up on the bottom right, it is sorted on the 2nd column. That's why you see the branch names or the suburb names, Brighton, Downtown, Minus, Perry Ridge, Redwood, and Round Hill, are sorted alphabetically. So that's like lexicographical sorting. The B, then the D, then the M, then the P, and so on. If you build an index on this column, then that index will be called primary, because it's built on the column that is used to sort the table. And of the primary, there were two types: primary dense and primary sparse. The primary dense is an index which holds one instance from every value that appears in the column. For example, if you look at the second column again, it says Brighton, Downtown, Minus, Perry Ridge, 3 of them, Redwood, and then Round Hill. If you look at the index, which is what appears on the left of the image, where it says index in memory, there is Brighton, there is Downtown, there is Minus, there is Perry Ridge, there is Redwood, and there is Round Hill. So from every instance that appears, from every value that appears, one instance is included in the index. So even though we have 2 Downtowns, we included only 1. We have 2 Perry Ridges, we included only 1. Sorry, 3 Perry Ridges, we included only 1. Okay? Now, the assumption is that this way you can answer any query faster by looking at the index and instead of looking at the relation. In fact, there is some type of queries that will save you loading the relation at all. For example, if you get select star from where branch equal to Heliopolis, you just need to look into the index to decide that there is no Heliopolis, and consequently you will never load the relation. Now let's imagine this is a big relation, as we discussed before, with hundreds of thousands of rows and tens of columns. So that's a lot of savings. And instead of loading something that is huge, now you load something that's quite small, which is the index. Because as you should have noticed by now, that the index actually is quite small. Because I'm going to include one value, one instance from every value, and just a pointer to where that row is. So the arrow that comes out after Brighton is telling me where Brighton is, which row. Okay? And if we divide this into the table into pages, which page on this and which row in that page. So that the total amount of space occupied by an index is quite small compared to the total amount of space typically occupied by a large table. Okay? Now, any query I get from now on, since I have this index, I will use the index. If I get select star from where branch name equals or branch location equals the second column, I'm going to use the index. If I get insert, I'm going to use the index to figure out where to insert it in. If I got insert, into this, and the values passed, say Heliopolis, I know that the H has to come between the D and the M, the Downtown and Minus. So I know roughly where should I insert the Heliopolis branch. Okay? If I get a delete, delete from where equal to Redwood, I know where is Redwood. So I'm gonna, from the index, I will follow the arrow and I will go to this row that says A-222 Redwood 700. So I will be using the index all the time once I have an index. The second type of a primary index is called a primary sparse index. Again, this is an index built on the column used to sort the relation. But in this case, we're not going to have one instance from every value that appears in the index included in the index. Instead, we're going to skip some in a systematic way and include one. In other words, we could do it like this. We could pick the first one and then skip 10 rows, and then pick number 11 and then or 12 and then skip another 10 rows, and then pick another row and then skip another 10 rows, and so on. So this is what you see here on the left side of this image. Brighton, Minus, and Redwood were picked, and the rest were not included in the index. That's why it's called sparse. It doesn't have everything. Now, Will we be able to answer queries and make benefit of this index? Yes, of course. But obviously, the benefit here is less. Let's say I get a query select star from where branch equal to Brighton. Well, I'm lucky Brighton is in the index, so I will track the arrow that points from the right of Brighton to the row that says A217, Brighton 750, and then I will scan in the table to find if the next row is also Brighton or not, and then I will stop because the next one is downtown, so I will include Brighton row in my result set. Okay? Now, let's say we got the query select star from where branch equal to Perry Ridge. Perry Ridge is not appearing in my index, but since I know this is a sparse index, it could exist in the table. It just was not picked to be included in the index. So I have to go to the table between the arrows that's coming out from minus and Redwood, which is the row A-215 minus 700, and all the way till the row A222 Redwood 700. And I will have to scan linearly those rows included within these two arrows to decide if Perry Ridge exists or not. And in this case, obviously, I will find Perry Ridge and I will include the three rows in my result set. So we are still winning. We are not necessarily, or not most of the time, not scanning the whole table. We are just now scanning parts of the table, doing linear search in parts of the table because of the nature of the sparse index, or because of the property of being sparse. So why would we use it? We would use it if the table is so huge in size. Remember, we are running always in the database world with the assumption that we will get stuck because of the size of the data we're working with. So we started by saying that if the table is so huge, we could be in a position where it doesn't fit in memory. So we ended up coming with a solution which is to divide it into smaller chunks or pages or blocks. So we split it up into pieces so we can load one piece into memory. What if you create a primary dense index, you cannot fit it into memory? The table is so huge that even a primary dense index now becomes so huge you cannot fit it into memory. Is that a likely situation? Well, not very likely in the case of modern servers, but if you think embedded systems, for example, if you think of smart watches or your microwave or your fridge at home, where you decide for some reason to include a database of items, maybe the amount of memory you're working with is so limited. It could be probably in the few hundred megabytes instead of being in the gigabytes. So maybe the space is so limited that you cannot even afford a primary dense index. So what's the solution then? Is to actually use a primary sparse index. And if you cannot fit the primary dense into memory, most likely you will fit the primary sparse, because primary sparse are going to be incredibly small. And they will still save you some time because you will be able to isolate the range in the table that you should be looking in instead of the whole table. So it's still beneficial, but not as much as primary dense in that respect. There is also a disadvantage here, which is that if you're trying to delete something, we have discussed this scenario when we discussed primary dense in the previous slide. If you'd like to delete something and it doesn't exist, you will not know it does not exist unless you go to the table and look for it. Like, for example, delete from where branch equal to Heliopolis. Well, Heliopolis could exist between Brighton and Minus, but you will not know unless you go there and check for it that it doesn't exist. Here is something you can also do. You could layer indices according to this way of thinking. Layer indices one behind the other. So what you see in this figure, the table first on the bottom right, and then there is a primary dense index that points to the table, and behind the primary dense index there is another index created that it is sparse. So when I'm executing any query, I would go from the outside one, the most outside one, the sparse, to a specific region or entry in the dense to the table. Now, why would I need to do that? Again, think here big. Say the table has 200 million rows. You create a dense index for it, and it has 75 million rows. You want to go processing the index faster. So you put on behind the dense index another sparse one. Now perhaps the sparse one will have like 5 million rows. What that enables you to do is to quickly isolate the range in the dense index that you should be considering. And consequently, you will quickly also reduce the number of rows you will be checking in the table. So these are called levels or leveled indices. Okay? You could put a dense, behind it a sparse, behind it even another sparse. Okay? And you can do as many as you like, but obviously you'll have to understand the impact on inserts and updates and deletes here, and it has to be valued against how much you're winning in the search. Okay? But we would do this again for the same reason I discussed before. Why would we use a sparse index, which is that if the memory is not fitting your indices. So one way to handle the situation is to keep adding levels of sparse indices. And as you go away, one level away, or one level to the left, if you'd like, the entries in the sparse index has to decrease, so you make a gain. Like the example I was saying, you could have like a table that has, say, 600 million rows. You create a dense index and it has 120 million rows. And then you can create another sparse behind it that points to it, that has 50 million rows. And then you can create another one behind it that has 10 million rows. And then you can create another one behind that has 5 million rows. So you go from the 5 million rows sparse index to the 10 million sparse index, and consequently you're narrowing down a lot your searches quickly. Okay? This is almost like, if you like, and we will see this actually very soon in the next lecture, it's almost like building a tree, if you like. Okay? Where the root is at the far right and the leaves is at the far, the root is at the far left and the leaves are at the far right of the screen. Okay? We have a name for this. This is called second level because it's behind the first level. And this will be a second level sparse, obviously on a primary field, or on a primary dense, or it could be a second sparse on a second sparse, by the way. Okay? So both of them will work fine. So here are some takeaways. A primary index is an index built on the primary column, which is the column typically used to sort the table on the hard disk. Another takeaway, describing an index as being dense means that the index has at least one instance from every value appearing in the column we are building the index on. And I could add here that value is going to be, in the simple scenario, the first value that appears, and this is what you see in the previous lecture slides. So when we had Pereridge, I pointed at the first Pereridge. The fourth takeaway is that describing an index as being sparse means that the index has a small percentage, typically 10% of the values, appearing in the column we're building the index on. Now, you must be asking by now, okay, we have been doing these indices or creating these indices on the column used to sort the table. What if I'm interested in creating an index on a column that is not used to sort the table? Which makes sense. I'll tell you why it makes sense to ask this question. If you remember from your database 1, you were told that there is something called an auto-generated ID that most database engines support. And that is a unique number that identifies the tuple or the row. Now, we will talk about this if we have time towards the end of the semester, because this is a good idea as long as you keep using that ID in your queries. But sometimes you're forced to have queries that is not using this ID. For example, if the user is searching for a product, they will not search by the product ID. They would search by the product name, the product category. And these will be columns in your table. But the user does not know the ID, does not know if he's looking for like a Samsung LED 4HD TV, the ID is 11799. It doesn't make sense, okay? He will search by the title, Samsung, LED 4K, Android TV, so on. Okay? So if you would like to speed such a query, then you create an index. But you're creating an index now on a column that is not used to store the data. If you are creating such an index, we have a name for it. It's called a secondary index. So a secondary index is an index created on a column that is not used to sort the rows in the table. Is that possible? Yes, but it comes with a penalty. Because what we gained in the case of the primary index is not anymore existing now. What we gain in the case of the primary index is that it is created on the column used to sort the table. So the values are progressing. If they are strings, they are progressing according to lexicographical ordering. The A's, then the B's, then the C's, then the D's, then the E's, and so on. Okay? And if they are numbers, they are progressing by value, 10, 20, 30, 40, 50, 60, 70, 80, 90. But now if you go to a column that is not used to sort the data, the values in this column will be scrambled. You will see 10, then 5, then 3, then 20, then 23, then 7, then 9. Okay? Because this is not the column used to sort the data. So the assumption that there is a linear progression of values, which is used in the way the primary index, whether it's sparse or dense, works, that assumption doesn't hold anymore. So the penalty we pay here is that when we create a secondary index, we will have to create a first level that is dense and sorted from the values of the column that we're building the index on. And then we can put as many sparse indices behind that as we like. So this is the picture I'm referring to here. Okay? This is an example of creating a secondary index. I'm creating the secondary index on the third column that has, and if you look at the right side of the table, it has 750, 500, 600, 700, 400, and so on. But you see, because this column is not used to sort the table, the values are scrambled. They're not either increasing or decreasing, they're mixed up. Why? Because I'm sorting according to another column, which is the second one. That's why you see Brighton, the B, then the D, then the M, then the P for Perry Ridge, and so on. So the sorting is done according to the second column. It's not done according to the third column. So if I would like to create an index so that I could actually see the values organized, so that I could load it into memory perhaps and do binary search, I have to have the first layer dense. Okay? So the most crude version of this would be just grabbing all the values in the third column and sorting them. So you will see 350, then 400, then 500, then 600, then 3 700s, then 1 750, and then 1 900. If you get too upset with the abuse of space here, because we had 3 700s, you could do what is showing up here in this figure, where I make the 700 point to a linked list of references that tells me where are the rows that have the 700. So as you see, I have one where it says A-215 minus 700, and the second one where it says A-218 Perry Ridge 700, and the third one where it says A-222 Redwood 700. Okay, so this is what this picture is really trying to do. It's basically, it is building a secondary index on a column that is basically not used to sort the data. So we have, as you see here, the values dense. We have a dense first level in the secondary index. We could create behind it as many sparse as we like. Now, since we created this index, we get now a query. So I say, let's start from where customer bank account, let's assume this is the third column, is greater than or equal to 700. So you load the index into memory, the secondary index, which is what appears on the far left, and you'll use binary search to find the value 700. Once you locate 700, you scan all the way till the end. So you're going to add in your result set the 3 rows of 700, the 750, and the 900. So your result set will consist of 5 rows from the table. Okay? Again, these arrows that points to the table from this intermediate list are nothing but where is this row, which page on disk, and which row in this page. Okay? So it's going to be some addressing mechanism. Now, we could, as I mentioned, create a second level secondary index. Okay? A second level secondary index is a sparse one which must point to a dense secondary index of the same column. And I've already discussed that. So here is the fifth takeaway. A secondary index is an index built on the non-primary column. Here is another takeaway. A secondary index first level must be dense. We gotta get all the values sorted. The key about this, we're saying dense because we're interested in sorting them, to have them from the smallest to the largest. And then we can do binary search. Okay? Without that, we can't. Now we come to the very important discussion of this notion of page versus block. What's the story here? Okay? Now, you will be a little bit surprised of how things actually develops here. Now, here is the thing. To understand what is the optimal size of a page or a block, you have to understand how magnetic hard disks work, which is basically the hard disk you have in your laptop or in your computer at home. Okay? If you open it, I hope you don't, because you're going to damage it if you open it, but if you open it, the hard disk case, you will see that it consists of platters, or what you could think of as dishes. This is what you see up. You see in the left image here. Those platters, there are many of them. And there is a head that reads from the platter. What it reads is what's underneath the head exactly. And usually, not usually, but it is the case that the head, the reading head, is connected to what's called the arm or the boom. This is what appears on the right image. This thing moves, the boom moves to the inside and outside. And in the same time, the platters can be rotated through the spindle. So there are two movements here. Movement around the spindle axis, and the boom is moving into the inside and to the outside. Now, why are we discussing this? You see, hard disks are an example of what's called electromechanical devices. They are devices that are made up of mechanical parts that are controlled electronically. And electromechanical devices where there is physical movement involved, and indeed we have here physical movement of the platters and of the boom, because of friction, because of electromechanical limitations, they're much, much slower than electronics. In fact, they are 1,000 times slower, at least. Now, that creates a problem for us, because if you would like to speed up the execution of any query, you would like to have a fast access to the data. But you can't have fast access to the data if your hard disk is 1,000 times slower your electronics or your computations. So, to decrease the impact of using such an electromechanical device, what we will try to do is to make sure that when we move the boom, consequently all the heads, to read from the hard disk platters, then we will need, and what we will read is meaningful to us. In other words, we're going to store the information that belongs to the same block, or let's call it with the proper name now, page, on the disk, in the cylinder, where a cylinder are the set of sectors that reside on the same perpendicular axis. That's what shows up here in this image on the far right, where it says cylinder. The cylinder is all the sectors that are underneath each other. For each one of those platters, there is usually a top surface and a bottom surface. That's why if you look at the boom, you will notice that there is a head at the top and there is another one at the bottom. Now, those sectors, or basically what defines a sector, is
what the head can read. So if the head can read in one shot 16 kilobytes, then the top and the bottom of the platter will hold 32 kilobytes in two sectors, a sector at the bottom and a sector at the top in the same physical location, but one on the top and one at the bottom. So basically what we can read in one shot, and one shot means after moving the arm and stopping at a specific location on the disk, are all the sectors underneath all the heads at the same time. Now, if we had stored our page or our file in separate, spread out locations throughout the hard disk, that means I will move the boom many times, or this arm many times, to just get the content of one file. But that will be an additional electromechanical movement or hard disk movement that we want to avoid. So instead, I will store the file content in the same cylinder, so that I can get all the content by moving the head, or moving the boom and the spindle to stop at both at the right location, so that everything I read from all the heads I have and all the arms are meaningful. They make one file. Okay? Let me try to give you a little bit of a concrete example. So let's say I would like to store this image on the disk. Now, and let's say that the image is huge in size compared to the sector size. So say the sector size is 32 kilobytes and this image is 10 megabytes. So it will be cut to pieces and stored on separate sectors. This is how a file system will do it. So that's basically what we're going to do. We're going to cut it into pieces and put it on different sectors. But to try to minimize the boom movement, this is what we're going to do. Yes, I'm going to cut it into sectors, but I'll put it into smaller pieces, but I will put all the pieces on the sectors that are beneath each other, and that will be a cylinder. All the sectors underneath each other together make what we call a cylinder. So I will store all of these pieces of an image that I have cut it into one cylinder, and instead of just sectors spread throughout the hard disk, they all will fit on one cylinder. If I can, obviously, maybe I can't, but if I can, then I'm going to do that. Okay? Why am I doing this? To decrease the need to move the boom again to another location to read the rest of the data. Okay? Now, here's the thing. In the database world, everything is paged. The table is paged, which means it's divided into pages. The index is paged. The index itself is paged. All the levels of the index are also paged. Everything is paged. Even if you remember from database 1, materialized views, they are paged. Okay? Now, it's not just they are paged. The size of the page is actually the size of the cylinder, to make sure that we are moving the boom as little as we can. Only when we need to read a new page, we move the boom. Okay? So, historically, in the database world, page sizes ranged from 16 kilobyte to a little bit more. And nowadays, it's 64 kilobyte, and few hard disks are now standing at 128 kilobytes. Now, if you're trying to put the pieces together, that's should be a little bit surprising, because this means if I have a table that is 400 megabytes, say, of data, millions of rows, okay, 400 megabytes. If you're asking me, okay, how many pages will it be stored in the 400 megabytes? Well, divide the 400 megabytes by 64 kilobytes, which is the page size, you'll get the number of pages that this table is stored in on the disk. Okay? Now, and this is the best thing we can do to avoid excessive mechanical movement. So here is the takeaway. Tables and indices are paged. Page size is related to the cylinder size. Now, let's go through an exercise of discussing what we have been discussing with paging now in mind, because paging is very, very dominant as a technique in the database world, and it causes all kinds of issues. Okay? So what you're looking at here, a relation on the right side, and then a dense index built on this relation. Okay? Now let's talk about this pointer before we move on. Just you're on the same page with me, because sometimes students are not really grasping the idea of this pointer. If I create my table is made up of text files, just plain text files, the pointer that you're seeing that has the title page, comma, row, the page is going to be just the file name on disk. And perhaps even the path to the file, which directory it exists in. And the row is going to be the row number. And that's basically it. Now, if you're not storing your table as text files, if you're storing them as binary content, you have to find the address of the row in the page in order to actually be able to extract the row. And the page itself will be just some binary file on disk. Okay? So I hope it's clear. Now, believe it or not, historically the first implementations of databases were all comma-separated values files. Now, comma-separated value is basically having a row, a tuple, stored in a row in a file that's made of text, and the values are separated by commas. That's why it's called comma-separated values. So if I have 3 columns, the age, the name, and the phone number, so it's going to be like 20, comma, 20 is the age, comma, Ahmed, Mahmoud, the name, comma, phone number, 0, 1, 10, whatever. Okay, so that's the comma-separated values. So if you store your table as comma-separated values, it's going to be the file name, the file of the name of the CSV file, and the row number inside that CSV file will be the row that you're looking for. Now, again, we're going to page everything. The relation is paged, the index is paged. In the case of dense index, as long as I'm pointing to an instance of every value, maybe it's okay. But let me, because other scenarios, and then we'll come back to this idea. Here is how now a sparse index will look like. Again, the sparse index is paged. Okay? The table is paged and the index is paged. Now, by now you should be thinking, if you're trying to think of the code, you should be asking me, like, okay, I'm going to reach to the relation pages from the sparse index. But how do I know where is the sparse index? Pages, right? Like you have the page, comma, row information that takes you to a specific relation page or a specific page of a relation in the sparse index pages. But how would you know where on the hard disk are the sparse index pages? And for that, either you store it in a metadata table inside your schema, and this is why Postgres has its own metadata tables that I've talked to you about earlier. Or you can develop some kind of a scheme where you say, when I create a schema, I'm going to create a directory on the hard disk with the name of the schema, and there will be a directory inside that directory that has a file that contains the names of the pages of the sparse index. Or you could develop a third way if you develop a naming convention for those sparse index pages. So for example, if the sparse index name is index_employee, you have index_employee1, index_employee2, index_employee3, and so on. Similarly, if we create a second level sparse index in front of a first level sparse index, it is as well will be paged. Now, why are we paging again? We are paging because we would like to minimize the hard disk movement. And we also have a secondary goal here, by the way, which is that we want to make sure that the page fits in memory. Obviously, it will fit if you're working on a server that has 4 gigabytes. But if you're working on an embedded system, again, like your smartwatch, the memory is quite limited. So you need to be able to fit the page to be able to use it. And if you page everything, then most likely you will be able to load it into memory. Now, let's talk about this trade-off of using sparse versus using dense. I've already kind of alluded to this before when I discussed with you that sparse takes less space, but we will be going to the table more. Dense takes more space, but we might in some cases even not go to the table at all and answer the query passed to us from just looking at the dense. Okay? This is what I mentioned here. In the case of the dense, you can tell if any record exists without accessing the relation file. Okay? In fact, there are many things we can do with the dense that will save us completely, prevent us or enable us to completely avoid going to the table. Like, for example, if you're running a SQL with aggregate functions, and you know that your primary length index is not just built on a column that is the one used to sort the data, that column is also unique. And since the rule for the dense index is to pick an instance from every value, and since the column is unique, if you would like to count the number of, say, where name is Ahmed, okay? And if you find it, you'll find it once. Or if you like to count within a range, like say for example, all the first names that starts with A, you would like to find how many first names that starts either with A all the way till C. So all the A's and all the B's and all the C's, all the first names that starts with an A and all the first names that start with a B and all the first names that starts with a C, that starts with a C, okay? You can get all that from the dense index. You don't even need to go to the table, okay? Now we start to do some real simulations of what actually happens with real data. What's the issue here? Having a column unique is a rare case in the database world or in any schema you design. When you set a constraint saying that this column is unique, that is not the norm. The norm is that we will have repetitions. If you even think of names, if you even think of first names and last names, you will see repetitions, okay? How many individuals you have met that are called Ahmed Muhammad, okay? Or Ahmed Muhammad Mahmoud, or Muhammad Ahmed, or Mahmoud Muhammad Ahmed? Quite a lot, okay? So how many people have you met as well who live in Abbas A'ad, or whose age is 20? Quite a lot. So this notion of working with unique data, it actually enables us to do things much faster. But the problem is, most of the cases we have to live with and suffer actually from duplicates. Duplicates in the database world will always cause us trouble. Okay? So let's see some of the troubles here. If you're building a dense index and you decide to do, obviously this is a primary dense because you have the values sorted in the table, I mean on the right side. One way to implement it, that's if you're trying to avoid all troubles, but then you're going to waste space, is to include all the values. This is valid. Okay, this is valid because the rule for the primary dense index is that you should have at least one instance from every value. But you can include, I'm saying at least, but you can include all of them. That's what you see here. Okay? You're pointing to everything. But now you're wasting space because you have 10, 10, 10. Why not just 110? You have 20, 20. Why not just 120? And 30, 30. Why not just 130? Okay? You would think to do this optimization to decrease the size of the dense index. So you will do this. You will say, okay, I will point to the first occurrence of the value. So I got 10, 10, 10, I'll point to the first 10. I got 20, 20, point to the first 20. I got 30, 30, 30, point to the first 30. But notice now the problem. If you look at this, you have just introduced a horrible bug in the schema or in the database. Because there is no way now you could reach to the page that has the two 30s. It's just impossible. What's the problem here? The problem is you forgot about the duplicates. If you say I'm going to point to the first entry that appears of some value, the first time it appears, and you get lots of duplicates, and the duplicates span more than one page, you're going to miss all those pages that are full of duplicates because you're not pointing to them. Okay? So if you get a query select start from a value equal to 30, you're going to return one row in the result set. You should return 3. You must return 3. Okay? Why are we having this trouble? Because of duplicates. And we will see this popping throughout the course. That duplicates always, oh, it's a trouble. We have to care about duplicates, we have to worry about duplicates, we have to come up with special rules for duplicates. So, to fix this, we're going to set a special rule that, yes, I'm going to point to the first entry that appears from every value, but I also want to make sure that I am pointing to a value in every page. So in this case, my primary dance that I was trying to optimize will have a little bit more of values, will have some duplicate values, because if the duplicates are spanning pages, like in the case of the 30, I have to point to an entry there to get access to that page. And obviously my code that will do the insert and select and delete has to change, because if I'm inserting now another 30, I have to find where to insert it, and it has to be between the first 30 all the way you have space till before the 40. Anywhere between those in those pages is okay. Now, let's say we decide to just stick to the rule that we are going to point to an entry in every page. And we are not going to do the rule where it says I'm going to point to the first time I see a new value. That will be the scene we're looking at here. The relation on the right and the sparse index on the left. Now, I'm not showing you all the details of the sparse index, the other entries. And let's say the query we're working with is selecting the rows with value 20. Now, I'm showing this example to highlight that based on how you decide to pick values, your code will differ. Because here, if the rule you're enforcing is to pick to point to a row in every page, select star from or value equal to 20 will get you this 20 that you are referencing in the third page. But since you're only here enforcing that you need to point to every page, you're not enforcing that you will point to the first entry, the first time you see an entry. If you don't go back to the previous page, which is the page that is pointed to using the second 10 in the index, or the second page of the table on the right, if you don't go to that to grab the first 20, you're going to miss it. So the correct result set should be two 20s, or two rows. Every one of them has a 20. Each one of them has a 20. Now you're going to return a result set of one row that has a 20. Okay? So, the same thing for the 30. If the query selects star from or value equal to 30, you are pointing to a page that has two 30s, but you need to check the page before it, and perhaps even the page after it to make sure that there is no more 30s. The page before it, in case there is a preceding 30, and there is actually one after the 20 in the third page in the table, and you need to check the page that has a 40, because there could be a 30 there as well. Okay? So, as you see, duplicates start to cause us trouble because we don't know where they start and where they stop. And you have to always check before and after your found result to make sure that you're not missing anything that you need to include in the result set. So let's study how the deletion is going to work if we're having a sparse index. Recall, a sparse index means we're not going to have all the entries in the index. We're going to only have a subset of the index. And I'm showing you here actually more than what you would typically have. What you would typically have, as I mentioned earlier, about 10% of the entries only in a sparse index. But just to illustrate my example here, I'm going to use a sparse index that only is skipping a few values. So it's skipping 20 and 40 and 60 from the page. So it's basically picking one value and leaving the other. Let's say we would like to delete. What is the impact of deletion? Let's say we would like to delete the record 40. Well, first we have to find it. So we're not going to load the table. We have an index. We're going to make use of the index. Somehow we will access the first page of the index. As I mentioned before, there is a number of ways we can identify where are the pages that belongs to this index. So we will load the first page into memory, the one that has 10, 30, 50, and 70. We'll do binary search in memory, and we will find that we have these entries, and if 40 exists, it's going to be between 30 and 50. So we follow those two pointers, the one that's coming out from 30 and the one that's coming out from 50, hoping to find the 40. We will start with the 30, we scan down in the 30 page and we will see the 40, and then since there could be duplicates, we will have to go to the 50 page as well, and since there's no 40 there, we will stop. So deleting here 40 is actually not costing us a lot. We will just load one page that belongs to the index and two pages that belongs to the table. 40 exists in the first page that we're going to load. We will delete it, but nothing else will change in the index because the 40 was not in the index in the first place. So we're happy. 40 will be gone and everything stays the same. We loaded 3 pages, one index page and 2 table pages. We modified only one of the 2 pages that belongs to the table, which is the one that had the 30 and the 40, and we write it back to disk. Again, remember, since everything is paged, everything on disk. So later on, we'll actually perform detailed analysis of this loading of pages from disk. But for now, I'm just introducing the idea. If I ask you how many pages did we load here, it's only 3. How many pages did we modify or write back to disk? It's only 1. What about deleting 30? Let's say we would like to delete 30. Again, we are going to load the first page of the index. We'll find the 30 right away doing binary search. And we'll follow the pointer beside 30 to the second page in the table. We will load that, we'll find the 30, and we will remove it. But once we remove it and it's gone, now we will have to update our index because we have to have at least one reference pointing to every page. And since there will only be 40 in that page, we will have to update our index with 40. So consequently here, we will load 2 pages, one for the index and one for the table, and we will modify both of them, writing them both to disk afterwards. So we did 2 page reads and 2 page writes here. What about deleting 30 and 40? We'll follow the same logic, but now when the 30 and 40 are gone, the reference to that page is also gone. And consequently, we could shift, or we need to shift the values up. So we'll move the 50 upward. And perhaps we could fill in this new entry that exists at the end of the first page in the index with some value that will come in the future. Okay? So here we will delete the page that belongs to the table, and we will update our index, which means after loading it from disk to memory, modifying it, we'll have to put it back on disk. So we are doing here 2 page reads or 2 page loads, a delete, and writing back the index page. So 1 delete and 1 writing back. Now let's move on to see an example of deletion from dense indices. So remember, in the dense index, all the values appear in the index, or at least one instance from every value. So now, by now, you should be getting a little bit worried, because what's going to happen now, every time we delete something, we have to change the index page. We have to write it back to disk. So here is something that's actually good about sparse indices. Sometimes we did that, sometimes we didn't, because if the value doesn't appear in the sparse index page, we're not gonna be worried about writing it back to disk, because we load it from disk, it's still on disk, there is still a copy on disk. We load it into memory to be able to search in it using binary search. But when we are done and we didn't change it, we don't have to write it back. It's still there on disk anyway. But now with dense indices, this scenario will not work. Every time we do a deletion, we'll have to update the index. So here's an example. If I delete 30, I will find the 30. I remove it from the the tables page, and I need to change it also in the index by removing it from the index, which means propagating 40 upward and erasing the 30, which means now I have to write that page back to disk. Okay. Now let's do insertion in sparse indices. We will find again that we are quite happy with sparse indices after this discussion, because again, insertion sometimes will be done without changing the index. For example, if you look at this example, if I would like to insert 34, so again I need to find where 34 will go. I will load that page, that the only page that exists in the index, into memory, and then do binary search to find where should I where should I insert 34. It's got to go between the 30 and the 40, so I track the reference coming out from the 30 to the second page in the table, which has this 30 only and an empty row, and I put the 34 in the empty row. Okay, so this is nice. We have free space. We don't need to actually change anything. And then we write back this tables page, the second one, where we inserted the 34, we write it back to disk. What about 15? If we insert 15, well, now you start to see trouble. The reason why I'm saying that things are going to get complicated, because after loading the index page and figuring out where the 15 should go, which is between the 10 and 30, you're going to follow the reference beside the 10 to the first page in the table, and you will identify that, okay, I need to insert the 15 there. But the problem is, according to my example here, at most I could put 2 rows in a page. So I cannot put the 15 unless I shift the 20 down. Now when I shift the 20 down, I have to make sure that the index is properly set up. And that's what you see here. I shifted the 20 down, bringing the 30 even further down, and then I inserted the 20 as the first row in the second page, and that emptied a space for me in the first page, and I inserted the 15. But what I'm going to do as a result of that is I'm going to change my sparse index entry from 30 to 20, because if I'm keeping the rule that I will point to the first new value in the table, in the page, then 20 is the first new value now I'm working with. I haven't seen 20 before, and consequently, you have to update the index this way. Okay. Now you might have still kept the 30 as is, and you still point to it, because as long as you point to some row in this page, we are okay with it. It just depends on your policy, how you're actually building the sparse index. And in case you actually try to respect a certain policy that says you're going to point to the first new value that appears in the page, then you'll have to change the index page from 30 to 20, and consequently you'll have to also save that page later on to disk. Now there is one idea here I'm going to introduce that will show up over and over in this course, which is that this business of shifting is quite troubling if you think of it carefully. And if all those pages we were looking at were full below the page that has 10 and 20, we could end up in the worst case shifting all the rows one location down, or one row down. And that could have like a ripple effect that goes from the first page to the last page in the table. Consequently, one strategy that many database engines would do to avoid this kind of rippling effect of shifting downward, is to create temporary overflow pages. To put the 15 there and link it with the first page. So I would create a page, imagine we create a page to the right of the first page, and we link the first page to it, and that would be called an overflow page, where we put the new entries that are supposed to go to this page. We put it there in the overflow page, and we're doing this to avoid shifting everything down with a single insertion. Because imagine you get a lot of insertions, and many of them will cause things to shift down significantly. So you end up doing basically an O(n) operation with every insert, or every couple of inserts, or every number of inserts. So instead of that, we could use an overflow page. Now, will the overflow page stay there forever? Not really. Database engines who would employ this technique would monitor the traffic, the number of SQL statements coming to the database engine per minute or per hour, and when the traffic goes down, when there is little traffic going to the database engine, perhaps people, this is a database engine behind an e-commerce website, and during the night most people will sleep. Unless they are a computer scientist, of course, but most of the time people would sleep at night. Okay, so when people are sleeping, the traffic is low, database engine realizes that, and when it figures out that it will figure out that this is a good time to actually go and merge the overflow pages into the actual table. Okay, this is just one way to avoid this, ripple effect of shifting down things. Okay, this is an example of what I was trying to say. Try to insert 25 after finding its proper location. Well, if I'm actually going to insert 25, I gotta shift things down. Okay, instead of doing any shift, what I'm going to do is once I find this location, I just put it in an overflow page. This overflow block or page are not going to be permanently there. When the traffic goes down, this will be merged back, which means most likely it's going to be put just above the 30. If at that time the situation was still that was still possible. Okay, now I'm not going to cover insertion in a dense index. We will run into all the cases we just described, except it's more expensive because we're more likely to shift things down, because we have now the dense index with all the entries and also the column with all the entries. So if you're going to shift down in one of them, you're going to shift down in the other. You shift down in the table, then also you shift down in the dense index. Okay, so we run into the same kind of problems. So and generally it is more expensive because of shifting down in the index. Now let's discuss secondary indices and how they could read duplicate values. Now remember, a secondary index is an index built on a column that is not used to sort the table, just like the table we have in front of us here on the right side. If I build an index on this first column, which is obviously not used to sort the table because the values there are not sorted, we said that the first level has to be dense. Then we run into an issue now when you have duplicate values. Because when you have duplicate values and you're just going to blindly copy all of the entries in this column and create a dense index out of it, you'll have lots of duplicates. This is what I'm referring to. I grabbed all the values and I sorted them, and I got these 3 10s and then 2 20s and then 4 40s and so on. Okay, and we previously said that in real life, duplicates are very common in many situations, in many data types, in many entities that you identify. There will be duplicates. Okay, that's why we ended up generating this notion of a unique key in the database way of thinking, just to be able to distinguish between entries. Okay, now you run into trouble when you look at this. You're wasting a lot of space. Why am I having 3 10s? Isn't it enough to just give the references and say just 1 10? So here is the 10 and references, a list of references. We've seen this before. A list of references, where the 10 exists, and then 20, and a list of references where the 20 exists, and then 30, and a list of references where the 30 exists, and it goes like this. Okay. So the problem here is that we're wasting space and we're wasting search time. Because if I'm looking for 20, I have to skip all those 10s before reaching the 20. If I'm looking for a 40, I have to skip all those 10s and 20s and duplicates just to go to the 40. Okay? So here is one option that I was describing. You put the value and beside it a list of references to where this value appear in the pages. But hey, remember, we also said that everything is paged, including the index. It's including the index. So now we run into an issue. I hope you can identify it. Can you identify it? Just look at the index now. Everything is paged. So the index also consists of pages now on disk. What we need to make sure of, and actually we will not be able to make sure of, the problem here is that we need our value and set of references to be contained within one page. Otherwise we'll end up loading more pages just to make sure that, or at least always one more page to make sure that there are no continuation of references later on. Okay, this is the same problem we've seen before. What we're looking at here is that there is no guarantee that my page size will fit me perfectly, in the sense that if you look at the first page of an index here, it has the 10 and then 3 references to 3 rows where the 10 appears, and then 20 and 2 references to where 20 appears. Let's say that the page size only enabled me to store the 10 and the 3 references to where the 10 appears, and then the 20 and then 1 reference to where the 20 appears. And the second one is not possible to store it in that page. So what we end up doing is going to the next page and adding a 20 there with the second reference to another 20. Okay, what that means, because everything is paged now, if we use this strategy and let's say our query was select star from or value equal to 20, it is not enough to actually load the first page. When we see the 20, we have to load the second page as well to make sure there is no more 20s there. Okay, because if we cannot put it in there, we will put it in the next page. Okay, now here is another alternative that's described in your textbook that people tried at one time, researchers tried at one time, and then they just stop doing it because it's a maintenance nightmare. And instead of keeping the value in the list of references to where the value appears, to the rows where that has this value, like the 10 for example here, what we do is we will link by adding a pointer at the end of the table that is not really visible to the programmer of the table or the schema. It's only visible to the database. We will add a reference to where is the next 10, and that's what you see here. And then from there is a reference to the third 10. And in the third 10, there is a null where it says there is no reference. It looks like a null value, okay, because there is no more 10s. So we will link them through an additional column that exists, and we fill in with the next value, which is basically the next row to go to. Okay, obviously we have a big problem here, which is that this is very difficult to maintain. Okay, and especially if we're going to shift things up, all of these references will be invalidated, so we have to go and fix them. Okay, so or if we delete an entry in the middle, like for example we have 3 10s here, one at the top, one at the bottom, and one in the middle. Let's say we delete this one at the middle using some other column. Now we have to fix the references. We have to figure out what is the first 10 and link it to the second 10, which is going to be at the bottom, which is in the second page from the bottom. So now we go to another maintenance nightmare. Okay, so as I mentioned here, this needs an additional field that's going to be added. You need to follow the chain, but it's a maintenance nightmare, so people stop doing this. So here is the 8th takeaway. Sparse indices are generally more efficient than dense indices. Holding only 10% of the values, the index gets updated less often compared to the dense index. Then that's why a sparse is often considered more efficient in terms of the insert and delete and the update. So what we have covered up till now is, we've introduced conventional indices, we've discussed sparse and dense indices, we've discussed the notion of multi-level, we've discussed the problems that arises from you having duplicate keys, and I have discussed with you as well and showed you kind of steps how you would support deletion and insertion in these indices. We also discussed this notion of secondary indices that we could build as well, and we could have multi-level secondary indices as well. Now, the nice thing about conventional indices, these are historically the first type that appeared, is that they're simple to understand. I mean, they're very common sense. In fact, you could write it, or you could do this kind of manipulation or this kind of an index in any Java program or Python program you write. I mean, it does not require any more knowledge than what I just described, and most of it is just common sense ideas how you organize the data. Okay. Now, another thing about it that will become clearer as we see the other types of indices is that the index itself is actually quite simple. It's not that just how things are organized is simple. The index itself is just trivial, okay? It's the value and a reference, okay? We will see things later on that are way more complicated than that, okay? Now, because also it is so simple, we could, once we load it into memory, we can do binary search and find out the result that we're after. Because it's, just a simple array in memory, or if you like, just think of it that way. What's the problem here? The biggest problem is that the insert and deletes are expensive. The deletes create holes, the holes require defragmentation. The inserts require shifting things down, and consequently it's also a problem. What we will look at next is a modern index that appeared in the last 10 years that is built on the idea of conventional indices. It's kind of a child of conventional indices, if you like, or the grandchild of conventional indices. Okay, so conventional indices as a concept is very important to understand because they are the building blocks of everything that we're going to see later on. There's a lot of what we discussed today we will refer to and repeat in different contexts later on. But no modern database engine would support a sparse index or a primary dense index because it's too trivial. And plus, they come with the problems, as I mentioned. The problem of shifting and the problem of fragmentation, they're not easy to solve. And when you talk about, tables that have hundreds of millions of rows, that becomes really a big problem. Okay, so there are other indices we will study that solve this problem. So conventional indices are not anymore there, but the BRIN is the closest thing to a conventional indices that we have nowadays. So it's a proper, actually, time to talk about it, because this is really, a twist on conventional indices, if you like. Now, this is called a block range index. So I want you to remember that it is really very useful when it comes to working with ranges. Okay? Generally, a BRIN index is nothing but a sparse index, but a different sparse index than what we have seen before. But it's a type of a sparse index. Okay? What's unique about it, what's different about it, is that even though it's a sparse index, we're not going to maintain a single value, we're going to maintain ranges of values. Okay? Which range are we referring to? We're going to store the smallest value and the largest value that appears in every page in the index. So if I have like 100 pages, I need to go to every page and find out the minimum and the maximum, and that's what I'm going to store in the index, the minimum and the maximum, as one entry. Okay, so minimum, comma, maximum, and then a reference to that page. Okay? Now, if you're building a BRIN index on the column used in sorting the table, that's the best scenario. Why? Because the values in that column are already sorted, because you're using it to sort the table, the rows. So the values are already sorted. So that means when you go and create a BRIN index, the creation process will involve the following. You will load every page that belongs to this table and grab the minimum and maximum value in that specific column, and then that's it. Okay? So constructing a BRIN index on the column used to sort the table is super fast. Here is an example of a BRIN index. What you see on the right are the table's pages. So I got only 4 pages I'm showing you here. And what I'm going to do in the BRIN index, I'm going to scan this column I'm building the index on and keep this minimum and the maximum values with me. And I can easily do that by looking at the first row and looking at the last row of every page. And then I put a reference to that page. So now I know that, if I'm looking for a value between 10 and 20, then I gotta follow the reference to that page, that first page in the table. If I'm looking for the value 55, I'm going to, say 45 for now, I'm going to follow the entry that says 40,50, and I will go to the third page in the table. Okay, so the ranges are actually helping me a lot. Well, if I have lots and lots of pages, okay, perhaps I have 500,000 pages in this table. That means I will have the first level in the BRIN index will have 500,000 rows, because for every page I'm maintaining the minimum and maximum, and if I have 500,000 pages, then I have 500,000 rows. That's ugly, and there is a good chance this is not going to fit in memory. So we could actually, or even if it fits in memory because we're going to page it, that's still a lot of rows to process. So what we can do is we could create a multi-level BRIN index. So 10 and 38 are the range of values that's bounded between the two rows in the leftmost block drawn here in the screen. So as you see, 10, 20, 30, 38. So I'm saying that those two pages, the ranges of in there is between 10 and 38. The smallest in the first one and the largest in the last one. Now, same thing for 40 and 70. Now when I get the query, so let's start from with value equal to 60. I will skip 10,38 and I will follow 40,70. And then I will again check the index, the first level BRIN index, for where is the 60, until I find it, if that's what I'm looking for. Okay, and that takes me, I will go to 60, 70, and that takes me, I follow the reference and I will go to this last page in the table that shows up at the bottom right of the screen. Okay, so BRIN indices are interesting because with these ranges I can know immediately if I'm interested in this page or not. Okay, so let's say for example I'm looking for 55. I don't even need to load the table to know that 55 does not exist. I can know that from the BRIN index. I will follow first 40 to 70 to where it says 40 and 50, and then I will realize I'm looking for 55, so I will move on to the next one, and the next one starts from 60. Since there is no 55, then it doesn't exist in this table. So one rule we're going to set with every type of index we discuss, we're going to talk about when should we use this index, because we are going to cover actually many indices, and every one of them is used, or it's best used in a very specific scenario. Okay, so this is the first one we're covering this semester, the BRIN index, and the question is when to use this BRIN index. Okay, I'm going to start with the second bullet in this slide. Let me read it. It says if you're doing lots of searches for data which belongs to a small range in a huge table that has a much wider range stored. What's the story here? The story is I have a range of values. Let's say it goes from 1 to 1 million. But I am running lots of queries that picks a very small, narrow range within this big range. So the range goes from 1 to 1 million. But most of the time I'm running queries that will return to me only, say, 100 or 200 rows, consecutive rows. So out of the million, I'm getting back 200 consecutive rows. Okay? So let's say, for example, you're storing, another example, if you're storing ages. So age will vary from 0 all the way till, say, 130, and that's probably like the longest someone would live. Now, if you look at your queries that you're finding to this database, and you find that wherever you're querying by age, you're only querying between 50 and 60, and you're ignoring the rest. You rarely query 100 or 90 or 80 or between or greater than 80. Okay, you're always querying, say, between 50 and 60. For some reason, for some weird reason, maybe this database belongs to an insurance company, and they're always interested in finding out what people are doing when they're between 50 and 60. Okay, or how frequent people die between 50 and 60, whatever. Okay, but you're finding always between 50 and 60, and the range spans from 0 to 130. We call this type of query low selectivity query because it will always return to you a small subset from the total number of rows that it could ever return. Okay? Now, for low selectivity queries, for this scenario, BRIN indices are great. Why? Because using the ranges, you can narrow down quickly, super quickly, Actually, it's extremely fast. compared to any other index we're going to study. You can narrow down where are you going to look in the table to retrieve the rows that belong to your result set. Okay? So this is exactly when you should start thinking about using a Brin index. For all other scenarios, don't use it. Okay? And we will see many other scenarios later on. Now, also, let's go back to the first point. Also, what you could do as a second option for you to use a Brin index, or a second reason why you would think why would you use a Brin index, if you are actually running aggregate functions on values, where you're not necessarily counting the number of values that appear, but you are trying to find out some statistical information about the values that shows up. Okay, for example, if you would like to figure out whether a specific number, say the number 50, appears approximately half the time in the table, or if you would like to sum up the values that appears within a certain range. So again, we go back to this range or low selectivity issue. Okay? Or you'd like to find out the smallest value in the table, or the largest value in the table. So there are aggregate functions that you could at least partially answer by looking at the index data, since you have these ranges. Okay? But not all aggregate functions, so you have to consider each one separately to decide. Okay? Now, means, for example, mean calculations are all very interesting, because there are approximate mean calculations that will enable you to calculate an approximate mean, not the exact mean, but an approximate mean, using the Brin values, the ranges that appears in the Brin. And instead of going to the table, touching the column, perhaps you have like 100 million rows to figure out the average, the mean. Well, if you can get an approximation of that using the Brin, that's fine. And there are actual techniques you could do to actually do that. So you can grab the values in the Brin, all the values in the Brin, and just sum up their values and divide by their count, and you will get an approximate mean, which is better than nothing. Not exactly an accurate mean, but it's an approximate mean. Now let me show you how you actually create a Brin. So every database engine you will come across will have many indices. That's why we discussed them in the course. Okay, we're talking here many as in tens of indices. As you will see later on with Postgres, there's a whole page that is dedicated to what Postgres supports. And they support something like 20 indices. Okay, if you count all the variations and the plugins. Now, for every database engine, because the standard for writing SQL does not specify how the programmer is going, or the database administrator is going to specify which index to be used. Every database engine will do it in its own way or in its own flavor, okay, in terms of the syntax. So in Postgres, if you would like to use Brin, what you're going to do is you're going to use the create index statement, just like we have seen before, giving it a name on some specific table, on some specific column, and you say using Brin. And this will happen, or will repeat, for all indices we look at. So later on we will say using B3 or using hash and so on. Okay? So this is how we create a Brin index in Postgres. And I have linked for you here the documentation that you should read regarding the Brin index implementation in Postgres. The takeaway is a Brin index stores the minimum and maximum values in each table page. It is efficient only in two scenarios: analytical queries and queries involving narrow range search on a column with a huge range of values. And here are the course references, as well as the pages that you need to read if you would like to check any of the details I have discussed today in the lecture.